So welcome everyone to our July call. We are very pleased to be talking to Michael Hunnekuhl today and talking about one of his many interesting and exciting projects. And Michael, it's always a delight to talk to you, and we really appreciate your time, especially at this late hour where you are. So we'll just turn it over to you unless Laura has any other announcements. Um,
Okay, yeah, thank you very much for your introduction, and I will share my screen. Just a minute. So I think you should see my screen now. Today I want to talk about a development of a mobile aurora spectrometer. This project has a long history. It started in 2021 as a side project, so in the beginning not with much effort on working on that. But yeah, I still worked from time to time on the project, and my motivation for this project was the question if it is possible to operate an affordable mobile aurora spectrometer for citizen science. This is not very easy because most spectrometers, especially if you want to use a calibrated one, is way too expensive for citizen science if you do not have any funding for the development. And my goal was, yeah, to develop and build a spectrometer that can be calibrated without any funding, and yeah, only a few euros to spend on that. So every spectrometer needs a diffractive element, and these diffractive elements are cost drivers for a spectrometer. You have different possibilities to implement a diffractive element. For example, a prism. It's very costly. Efficiency is high. Transmission gratings also very efficient, but also very costly. And an alternative that I choose is a foil transmission grating. Such gratings are very inexpensive. So the price for one element is in the range of €1. And the question is, if it is possible to build a spectrometer that can be calibrated based on such a low-cost foil transmission grating. And this transmission grating or other diffractive element is very important to split the light that is detected by the spectrometer. So as you can see here on the image on the left side is just an example how a monochromatic laser beam will be diffracted with such a foil grating. So you see here the transmitted zero order beam in the middle and the diffracted first order beam on both sides. So this is for a laser beam. On the right side, you can see the same grating, a little bit tilted with a white light source, and you can easily see that the white light is diffracted, and you can see all the color components in the white light. So in principle, it is possible, but the question is if the quality of the spectrum is good enough to use it for spectroscopy. At the beginning, I built a proof of concept model, very cheap, just to check the concept. So I have here a diagram that explains the concept. You have a straight light baffle spectrometer slit, which is simply made of razor blades, a self-built collimator, so old lens or old coated lenses that I had in my lab, for a transmission grating, and then a camera with a camera lens attached to it that is used to image the spectrometer slit on the sensor of the camera. At the beginning, I used two different approaches for the angle of incidence for the foil grating, 34° and 0°. You can see it here in this diagram, and use these two configurations to check if a spectrum can be recorded. So this is an image of my proof of concept. So it's very, very cheap. If you neglect the camera and the camera lens, the costs are in the range of 40 euros. So extremely cheap, built of paper and wood and a few magnets. It looks very easy, but it is possible to record spectra with such a device. So it's very important to measure the slit width of the spectrometer to align the spectrometer correctly and to estimate the resolution capability. And it's very easy. You can use a laser pointer pointed to the slit made of two razor blades and measure the diffracted beam behind the slit, and by measuring the distance between the different orders of the diffracted beam, you can simply calculate the slit width and also can check the parallelism of the slit. It is possible to manually adjust razor blades to a slit width of approximately 50 microns. That is possible, but if you do this, you have, of course, not much light to operate the spectrometer, and my goal was to operate the spectrometer with a slit width of 100 microns. That can easily be adjusted in a few minutes. You can see
Michael,
here
can
three
I ask you
examples.
a question?
Yes, of course.
So these foil gratings, do they have any calibration or spec on
No,
the
the only
grate?
spec the manufacturer give is the amount of lines per millimeter. They provide I think two or three different types. I use a type with 1,000 lines per millimeter.
And what you were talking about on the previous slide is measuring that, or it's actually measuring
What
the width
I'm
that
measuring
you.
here is the width of the or the distance between the two razor blades. It is You have to adjust two parameters for this spectrometer. First, the parallelism of the razor blades, so that the spectrum is not distorted, and you have to measure the width to estimate the resolution of the spectrometer. This is just a setup that allows you to measure the slit width, and this can then be used to estimate the achievable resolution.
Can
Yeah.
in my head I'm comparing this to a little very cheap similar spectroscope that we've made as like a kids activity, but
Mhm.
in the equivalent kids activity, you have the same foil grating, and then you basically poke a hole in some tinfoil at the front of
Yeah.
the grating, and in between it's like a cardboard tube kind of thing. So
Yeah.
I can see in this case, you have razor blades that you can adjust their
Yeah.
distance,
Correctly.
and then you've
Correctly.
measured um, the effects on the patterns that you're looking at for that distance.
Yeah. Correct. And I
Yeah.
use razor blades because they have a very, very precise, sharp edge, and this is combined with a very low price. And what I did not tell is that you have to blacken the razor blades for the
Yeah.
spectrometer. Otherwise, you get a lot of stray light, and that can very easily be done by holding the razor blade in a flame of a candle, and by this you can blacken the edges very precisely.
Cool.
So you can see here three examples for recorded spectra from fluorescence lamps. The one you can see here on the left side is a handheld fluorescence lamp that I use in the field to adjust and check and calibrate the spectrometer in the field. So it's very important because if you transport a spectrometer, you have to be sure that your calibration is correct during measurement. And if you calibrate it at home and then travel by car, outside and measure spectra, you have to be sure that the alignment is still correct. And for that, I use this lamp to check and, if needed, to readjust the spectrometer. Okay, you can see here on the left side again a calibration spectrum, and on the right side spectra of a cloudy night sky. Cloudy night sky with a slit recorded with a slit width of 100 microns. And what you see here is mainly light from artificial light sources, so street lamps. Here are a few early spectra are recorded. So you can see here the black spectra is just a calibration lamp. And the other curves are spectra from the night sky showing light from artificial light sources on ground. This was just a spectra that I recorded to prove if the spectrometer works in principle. So the spectrometer was not built in a way that the resolution is optimized and the sensitivity is optimized. I did that in the next model.
Michael,
I also, yeah.
Can I ask one question on the previous slide?
Yeah, sure.
So your feeling at this point is you didn't know the resolution, you don't know the resolution you can achieve yet,
Yeah.
whether you could separate auroral lines, which would be the goal.
Correct.
But
Yeah.
what I'm reading from your different charts here is that your calibration lamp, while it might be good for like an overall calibration of the wavelength, it's too wide for it's probably too wide for what you might be like the actual sensitivity is narrower than what the calibration lamp spectra would give. Is that correct?
Yeah, but at the end, I calibrated. I will show that later with Fraunhofer lines in the sun absorption spectra, and that is yeah, much better for calibration. I think I will show that later on
But
other
the
slides.
results with the night sky are like
Yeah.
promising at that point, right?
Yeah,
They're
and
narrower.
one important question at that point in the development was what exposure time is needed to record to record a spectra. Does it take minutes or just a few seconds? And that was very important to check in first test, and that was mainly the yeah, purpose of this measurements to get an answer for the question, how long do I have to exposure? I also did with a proof of concept model a test to look what is the maximum resolution I can achieve with the spectrometer. So I reduce the slit width to 15 microns, so the minimum I can adjust. And as you can see here from this spectrogram showing a spectrum from a calibration lamp, that you can see features with distances in the range of approximately one nanometer. So the sensitivity is quite good, but to be honest, this is not achievable with that first proof of concept model if you record an aurora, because you need much bigger slit widths to record a spectra in a reasonable time. Yeah, and these are results for sun spectrum and calibration lamp, averaged over 15 image line, was very important. I just skip back to an earlier slide. What I did not mention, the spectral lines are curved in the spectra, and this is a limiting factor if you want to remove noise in the spectra. So noise reduction can be realized, for example, by simply averaging image lines. But this is only possible in a simple way if you have straight vertical lines and not curved lines. And that was a limiting factor for my proof of concept model, because at that time I did not have had a software that can distort the spectra to get vertical lines. And the spectra here were averaged over only 50 image lines. So the overall spectrum has a height of several hundred lines. And this is a limiting factor of if you want to improve the signal to noise ratio. Spectral range is about 415 to 685 nanometers. So it covers the whole visual spectral range. And for that model, I could achieve a resolution of about 3 nanometers with a reasonable slit width in the range of 100 microns and better results with
What is
reduced slit
the
width.
comparison to like a Cadillac spectroscope for Aurora? It's less than 3 nanometers, I'd guess,
Yeah, of
but
course, of course. I think it's in the range of 1 nanometer for a professional spectrometer.
so you're not too far off though if you're
Well,
getting
this is a proof of concept
yeah,
model.
yeah.
The next model is much, much better.
Okay. All
So
right.
you will see better results. This was just the beginning of my project. And then I developed the second prototype. And one of the first things I found in the beginning of the development was that the angle of incidence for the foil grating influence the deflection angle. So if you tilt the foil, the deflection angle of an incoming beam changes. That is very important for foil grating because the foil grating is a little bit bent, so it's not flat like a transmission glass grating. And you have to choose your angle of incidence so that the variation of the deflection angle with variation of the angle of incidence is minimum. And my first proof of concept model was not very well designed. So my first prototype used an angle of incidence of 33 degree, and at that angle, the deflection angle changed quite strong if you tilt your foil grating. And I measured this curve with a laser beam and found that I have to use a different angle of incidence in the range of 16 degree, where the deflection angle varies almost does not vary with the angle of incidence. So bending of the foil have no influence on the deflection angle, and this will improve the spectral resolution significantly. And for that, I simply have to change just the position of the foil grating and tilted it a little bit more than in prototype 1. And I also add a cylinder lens in front of the spectrometer slit to reduce the horizontal acceptance range for the spectrometer so that it is able to record a spectra of a well-defined region in the sky. And this is an image how the second prototype looks like. So most parts are 3D printed at home. I bought a cheap 3D printer for that in the range of 200 euros, so very, very cheap. And designed the whole thing with a freeware cut tool. So I had experience in cut designing. I did that several years in my professional work. And was able to design and build this spectrometer prototype 2. So the most expensive part inside is the collimator lens from eBay. It costs approximately 20 euros, and that is the most expensive part in the spectrometer. The spectrometer slit is again built from razor blades, but now a little bit better integrated in the mechanics. I also integrated a cylinder lens in front of the spectrometer slit because I want to reduce the view angle for the spectrometer. I think it's very important if you have a spectrometer that you can point it to a specific region in the sky and record a spectra only for that region. And with this cylinder lens in front of the spectrometer slit, I could reduce the horizontal acceptance range down to approximately 1 degree. And the vertical acceptance range is in the range of 10 degrees. So you have a very, very small field of view in which you record a spectra. And this is an early result. So you can see here a sun spectrum, which clearly shows the main Fraunhofer lines in the spectrum. Yeah, that's further images. And yeah, at that point, I found that to improve the spectrometer, I have to find solutions for two very important tasks. So the first one was the spectral lines, as I said, in the recorded spectra are curved lines, and I had to find a solution to convert the recorded spectra into a synthetic spectra with straight vertical spectral lines to be able to average all image lines to reduce the noise in the image. And because I thought that this was a difficult development task, I prioritized other projects, and this spectrometer project paused for nearly 2 years. The second important task I have to address is I have to convert raw images to TIFF files in a customized way to control that the conversion leads to a spectra that generates spectral lines with heights that are that change linear with the detected light. And if you convert a raw image to a TIFF file or PNG, whatever you like, with standard software tools, you can't use the spectrum because you don't have this linearity. Each camera and also software tool that you can use to convert raw images to for example TIFF files will influence the conversion and it will not be linear. And for that I have to develop a software tool that allows me to fully control the raw conversion process so that I can be sure that the height of spectral lines varies linear with the amount of detected light. And because I thought that this was very difficult and would take a lot of time, I paused the project. But then, end of 2022, as we all know, AI systems were deployed, and they developed very, very high capabilities for Python code generation. And I used several systems. I will show later what systems to generate Python codes to address these two tasks by simply explaining my development goal in natural language, but very detailed descriptions, and ask the AI systems to generate the Python code needed to address these tasks. I start this development, as I said, without any Python code that I provided to the AI system. I only explained the development task with natural language, in my case in German. So it makes no difference if you use German, French, or English. They perform good in all languages. and I developed three different codes. One code for the raw data extraction, partly developed with ChatGPT 4.0 and mainly with Claude Sonnet 3.5, which was at that time significantly better in code generation. A different code for the distortion correction, so correction of curved spectral lines. Also started with ChatGPT 4.0, but then I got stuck in the development and changed to Claude Sonnet 3.5, which performed significantly better in code development at that time. And noise reduction that was a very simple program, just allowing to average image lines in the distortion corrected spectra developed with ChatGPT 4.0. And all this code was simply developed by explaining the AI system what they should develop without giving them any starting code. So one important thing at the beginning was the raw data extraction. As you may know, the sensor of a camera chip does not detect at every pixel position all lights. Each pixel simply detect one color channel, and if you want to convert a raw image into a real image, you have to interpolate the raw counts from all pixels to the positions where, for example, no red and blue light is detected, so that you get a synthetic image where each pixel gives you values for each color. I developed this raw conversion with Claude 3.5, and yeah, what does the code do? So first, you can choose a region of interest where the raw counts shall be evaluated. This is a region where the image shows a spectrum. Then you have to read out the black and white levels from the raw image. The black and white levels are not zero, for example, for the black level, and not the maximum count for the white level. They are camera specific. My code is able to find these values, and between these values, you count the light intensity. And the goal for the code was to transfer counts from this range to a full TIFF range, so 16 bits. And I will skip that because of time. What I also did is a linearity check. So the raw conversion have to be checked. So what I did is I took a set of images recorded with varying exposure times from a wide surface, and evaluated the raw counts in different regions, and plot that versus the exposure time. And when you do that, you can see that the averaged raw counts for the pixels really increases linearly with the exposure time, and that means that the raw counts evaluated with my program really scale linearly with the intensity of light, which is very, very important if you want to do any quantitative spectroscopy. And this cannot be done with simple raw conversion tools. So next step was to correct the curved spectral lines, and for that I developed a second code that distort these lines. This is an example of a sun spectrum. You can see here on the image a spectra of a calibration lens with the curved spectral lines, and to change these curved lines to straight lines, I use the following approach. I first average the central 21 image lines for noise reduction and detected the spectral line with the highest intensity, and do the same with groups of image lines above and below the central line. And each of these group of lines will then be shifted by the code to the so that the spectral line with the highest intensity fits with the spectral line with the highest intensity in the central group. So that means each group will be shifted slightly, and then the code interpolates this shifting to all image lines to correct the spectra. And this shifting is stored by the program and can be transferred to other spectra that are recorded after recording the calibration spectra. And this is how the corrected spectra looks like. So you get really straight lines, and this allows you to average all image lines to improve the signal-to-noise ratio in the spectrum. And here's what you get after all. So this is the calibration lamp I use for that. Here's the spectrum with the curved lines, and this is the calculated spectrum from this from the spectrum where you average over all image lines, and you see here that the noise is very low. This is 4 times stretched, and you see here that the resolution the resolution of the spectrometer is in the range of approximately 1 nanometer. So much better than my first proof of concept model.
Michael,
Yes.
could you actually talk about what caused the curved lines? I think I missed that, and I think like whether it was something mechanical or
That's a effect that is caused if you tilt a grating in the how can I explain it? I think the main reason for that is that the light path from the grating to the image depends on the the light path from the grating to the image varies with the position on the slit. It's mathematically a little bit complex. I cannot explain it very well, but the main reason, to put it in easy words, is that the distance from the grating to the image varies with the position on the grating, and that leads to these curved lines. And this is a typical effect for grating. It's called a smile effect, and this has to be corrected if you want to improve the noise of the spectrum.
Thank you.
So what are the lessons learned from the AI code development? So first of all, it is very important that you discuss any errors in the AI generated code with the development system. So you do not have to expect one should answer. So if you define a very complex task for Python code development, you should not expect that the first should of the system gives you an answer that is completely correct. So in most cases, there are some errors, sometimes only minor errors, sometimes bigger errors, and it's very important then to discuss simply these errors with the system. So you give them a feedback and tell them what errors your compiler gives you, and then iteratively you can fix these errors. In almost all cases, I had this works very well. So if you do not have a very complex code with thousands of lines, in most cases you can solve issues you have in the first answer from an NI. It is also very important to describe your task very detailed and precisely. The more detailed and more precise you describe your task, the better the answer is. It is also very important to give the AI system a feedback about your own knowledge so that it can explain what you have to change so that you can understand correctly what you have to do to correct an error. It is also very important that you tell the AI system that the AI system is an expert coder. This is very crazy, but if you do that, if you tell an AI system like ChatGPT that it can code very well, it will code very well. And if you don't tell the system to do that it is a good coder, it is not performing as good as it could. It is also very, very important to discuss code that is developed by an AI system with another AI system that is not involved in the development. So you give the code that is developed by system A to system B, and ask system B to explain the code very detail. And if there's an error, in most cases, system B will detect it and tell you what you have to tell the other system to correct it. You can also initiate direct conversations between the AI systems so that they can discuss in natural language an error, and you moderate this discussion and intake with both to optimize the code development. That also works quite well. And what I found is that for code development, in my cases, the system's Claude for Opus, it's a quite new one, Gemini 2.5 Pro, and ChatGPT o3 work best in code development. I got best experiences with Claude for Opus and Gemini 2.5 Pro, especially if you want to develop a very, very complex code. And long code, that means more than 1,000 code lines. I strongly recommend Gemini 2.5 Pro because I had some cases where I develop code with more than 1,500 lines and iterate the development in one single chat, and this is only possible with Gemini 2.0 Pro because of the very long context window of this AI system. This is also a system that can be used to discuss PDF documents with 100 pages easily. So prototype to field testing. In October 10 last year, I had the opportunity to view a very strong aurora here in my hometown near Hanover in Germany, and recorded the aurora with two cameras. And in parallel, I recorded spectra of the aurora with the prototype 2 spectrometer. Just to give you an impression, these are images recorded with approximately 10 seconds of exposure time. So the red aurora was very strong. It was easily visible as deep red with the naked eye. So yeah, I never saw such a red aurora here in my hometown before. Yeah, and on the right you see this spectrometer mounted on a tripod as I used it in the first field testing. The slide shows evaluated spectra of a green aurora recorded with 60-second exposure time. The left images show two spectra with a full range, and the right shows the image on the left stretched by a factor of 10. And there's also no background subtraction. As you can see here, you can identify a lot of very weak aurora lines, and also the two red lines around 630 nanometer are very, very well separated. So the resolution in this case is approximately 1 nanometer. And as you can see from the left spectra, it would also be possible to record such a spectra with significantly less exposure time if you do not want to have such a good signal to noise ratios. The aurora was not so, especially the green one was not very intense, so it was not visible as a green aurora by naked eye. So you needed a camera to to detect the green light. So I expect that exposure time would be significantly lower for really a bright aurora. The next slide shows two spectra for mainly red aurora, especially the lower part is mainly red and does only contain red component and the green one, but no other aurora line. That is different in the upper spectrum, where you also have a few other weak aurora lines in the spectrum. And yeah, the main message from this measurement is that it is possible to use the spectrometer in the field for spectroscopy. The image, sorry, the wavelength calibration. For this, I used a spectrum of a daylight sky. So I took a spectrum from a quite foggy sky, so no direct sunlight, and you can see in the spectrum intense Fraunhofer lines clearly detectable in the spectrum. And here on the right side, you see the signal from these three color channels separated, and you can clearly see that the three color channels overlap. So it is not possible to calculate the intensity of a specific wavelength just from one color channel. For this type of camera, I use a Canon. I think in the US it's called Canon Rebel 4TE. But this camera was modified, so this is an Astro modified version. So that means that the filter in front of the sensor is replaced by a filter with a much higher transmission for the high alpha light.
Michael,
Yes.
you might want to wrap up in the next couple of minutes so you have a
Okay.
little time for questions, and
Okay.
then we could hold a little more space for some details at the
Okay.
end if that works.
Just to show you the calibration. So it's a very straight line if you calibrate wavelengths against pixel. So very important, the performance. So spectroscopy, the aurora spectroscopy is possible. You can record a spectrum in less than a minute. Wavelength range 215 to 685 nanometers. Spectral resolution in the range of 1 nanometer or less. And very important field of view about 1 degree horizontal, so quite narrow, and 10 degree vertically. So outlook, what is the next step? Next important step is calibration of the spectral responsivity, which is not calibrated now. So that means if you want to calculate the ratio of spectral lines, you have to do a full spectral responsivity calibration to allow you to calculate ratios of spectral lines. At the moment, I can only quantify intensity changes in one spectral line. So if I record two spectra and the spectral line goes down by a factor of 2, then I can say that the light intensity also goes down by a factor of 2. But I cannot compare spectral lines. And to do that, I have to buy a calibration light source, couple it with a fiber in an integration sphere, and record the light from the integration sphere with my spectrometer. So first step, I was able to procure a very cheap 50 centimeter integration sphere that is illuminated by halogen lamp. And my plan is to replace the halogen lamp by a fiber coupled calibration lamp. And I'm waiting for an opportunity to buy a cheap one, because a new one is quite expensive, in the range of 1,000 euro, not affordable without any funding. But I think if I wait a little bit, I might be lucky and find a source that is not so expensive. And with such a source, I will be able to fully calibrate the spectrometer so that I can uh, measure spectra quantitatively. The only thing that I cannot do is calibrate the absolute intensity of spectral lines. So I cannot say this is 500 Rayleigh or so. That's not possible with the equipment I can realize. Yeah, thank you for your attention. And if you have any questions, just let me know.
Thank you so much. This is amazing, really amazing to hear about and to see all of the steps. And it must also be very gratifying that you got a storm to test it on.
Yeah.
Uh, we would welcome any questions. Yes, and kudos. What kind of long range goals or vision do you have for this project? It's
And
one
my
question.
my long range goal is to achieve a development state where I can record a spectrum quantitatively. So the main development step I want to achieve is to implement calibration of spectral responsivity, and as a second development step, to implement an adjustable spectrometer slit so that I can change the resolution in a observation campaign and adjust the resolution to the intensity of the aurora. So if I have a very intense aurora, I can reduce the slit width, improve the spectral resolution, and if the aurora gets weaker, my plan is to open the slit in the field, and that's at the moment not possible. I can only do that at home, but not in the field.
How can we help?
um, Helping me to find a source for a affordable calibration lamp. Maybe you know some people here in Europe who may have an old lamp that they want to replace by new one. So
Yeah,
far,
we've
I
been
did
messed
not.
around.
So
Yeah,
far, I did not found any source. I'm looking quite regularly, and I think I will at some time. At some time, I will find some device. I also had luck with the integration sphere. It cost just 200 euros. If you buy it new, it will cost, I think, more than 2,000 euros. And this was, yeah, um, very, very helpful to get that.
Mhm. Yeah, if you have specs or names of that kind of thing, I might know
Yep.
some people that could help
Mhm.
uh, find something around the world. So, other questions?
Hey, Michael, this is Jeremy. That's an amazing presentation. Thank you.
Hello, Jeremy.
I wanted to ask briefly, I know you're using a digital SLR and it has the Bayer filters, which affect, sort of the absolute measurement of spectral lines across
Mhm.
the sensor and so on. But is there a consideration for using a monochrome style astronomy kind of sensor? I'm thinking of like the ZWO sensors that are designed for deep field imaging with separate color filters. Thanks.
Yeah, I think this could also help to replace the camera by a monochrome sensor. I simply did not do that because I have none. So I have some monochrome sensors, but they are too small, and and I just use what I have. But you're right. To replace a camera by a monochrome sensor could also improve the sensitivity, especially if you use a sensor that can be cooled. That would improve the sensitivity highly likely significantly.
Thank you.
Yeah.
Anyone else? I had a question about, had another question, but I'm happy to yield if anyone wants to ask any questions. What about for other Aurora chasers who might be interested in trying something like this? Do you envision this more as an open project or, um, obviously up to you for sure.
Yeah, I would be happy if other citizen scientists or aurora observers are interested to help me in the development, or, for example, to test it in the field. One limiting factor here is I do not have many opportunities to test the system with a bright aurora. So there are only very few events in the year here, and having an observer in a better place who can test the system much more often would definitely help to improve the system. So um, I'm very interested in cooperating with other observers or citizen scientists who are interested in working on this project and help me.
Mhm. Awesome. Josh Summeter also put in the chat that up there in Fairbanks, Don Hampton, who you've probably met through this group, he's also Vince's advisor. He has a calibration facility at Poker
Mhm.
Flat up there in Fairbanks. So
Oh, okay.
that might be something if you are able to go to Fairbanks,
Yeah,
planning
yeah.
Fairbanks in October, to get in touch about this.
Yeah, that will be fine. I hope everything is going well for the travel. At the moment, it looks good. Yeah, hope let's hope that nothing changed.
Let's see, is there another question? Laura says thank you. And yes, thank you everyone. Understand if folks have to leave. I have one more question about whether any of your raw data extraction algorithms kind of have applications beyond this spectroscopy. It seems like that can be used to help quantitatively normalize between different types of cameras and their images.
Definitely, definitely. Yeah,
Yeah,
I'm
that's
also interesting to share the program. There's one thing I have to add. At the moment, the code is optimized for my camera and the Bayer pattern realized in my camera. So the Bayer pattern can vary between different camera types. And what I want to do is that I want to change the program in a way that a user can yeah define a camera in a graphical user interface and do the conversion with different types of cameras. And this is I don't think that this is difficult to implement that. And only have to look for data for the for the buyer pattern for different camera types, but I'm quite sure that I will find that somewhere.
that would also be something it would be cool. Aurora chasers could help test with different
Yeah,
cameras. If people were co-located, right, they would then be able to get very similar images
yeah,
from cameras, which is not currently possible.
yeah,
Um,
yeah. I think that's a program can be used for that.
awesome. And if you can see the chat, Donna also has a contact
Mhm.
working with the rural spectrum analysis. Um, so I think we'll wrap up here. Thank you so much, Michael. This is really interesting and wonderful work in so many ways. Yeah, really exciting.